Doing claims now about the mean. Now there's two different types of problems that are going to go on here. There's problems where normal distribution, we know standard deviation. That's the most awesome situation, but the least likely. Again, normal distribution is not that unbelievable. That, right? We know certain things do. Duration of pregnancies, human heights, believe it or not, SATs, IQs. We know these are normal distributions, and in fact, in each of these cases, we already know the population standard deviation. But in general, you're measuring anything. You're measuring things about tire life. Do you know the standard deviation ahead of time? No, you're going to use your sample. So whenever you're using your sample standard deviation, it's automatically T instead of Z. Remember, the two things you have to have for Z, it has to be from a normal distribution, and you have to know sigma. The normal distribution is not absurd that you'd know that, but knowing sigma is the one you're far less likely in reality. Again, I gave you some examples where we actually do know the standard deviation of a few things in real life. Okay, so we're going to start with one involving normal distribution and sigma. Hold on one second. Okay, we know that IQ, oops, of course I already got a bad pen. Oof. Oh my black. Yikes. I gotta have one with some juice in it. IQ is normally distributed with a standard deviation of what? Does anybody remember?
15.
Of 15. Yeah, we've done this enough times. Now, we know this. This is not in question. We're not testing whether IQ is accurate or not. What we're going to do is we believe that Mesa College is exceptional. We think Mesa College, is at least, a certain level. Now, to just simply say we believe Mesa College is above average, we come out with remember that, what is the mean for the population? It's 100, right? Well, what if we're on average 100.1? I don't think that's really, I don't think that's really saying anything. No, we believe that we're, really, really good, okay? We think we're significantly higher, okay? So, IQ is normally distributed. We believe Mesa students are higher than the average of 100. Like I said, if our students are only a tiny bit above average, just, we went out and measured 10 people and we got 100.1, that's not significant. What if we went out and measured 10 people and we got an average of 110? That would be significant. So we're going to figure out where's the line in the sand and all that stuff. We believe Mesa College students are above this. So now I have to come up with, and let's say we'll make it simple. We're going to test at the alpha equals 0.5 level, okay? That's the most common one. So what is our... Now, a lot of folks make the mistake of saying whatever the claim is, that is the null. That is not true. In fact, you know how often that's going to be true? Exactly 50% of the time. My claim is a strict inequality. That can't be the null. The null has to include the equals. Oh, so I am saying Mesa College students are better. Do we start by assuming Mesa College students are better, or do we need to prove Mesa College students are better? Which way do you think it works?
We have to prove.
Yeah, I'm going out there and I'm announcing to everyone, Mesa College students are smarter than everyone. It's not up to you to prove that we're not. It's up to me to prove that we are. Because I'm saying we are. So the alternative is that the Mesa mean, what's the national average is 100? Or I shouldn't say the national average, the average human being. So the alternative hypothesis, which is my claim in this case, is that it's 100. So if we're not smarter or better than everyone else, then what are we? The same or potentially worse? So what is the null hypothesis?
Less than or equal to?
Less than or equal. The burden of proof is on us to prove it. And by the way, it's easy. We go out and measure a whole bunch of people. That's the easy part. But anytime we're going to make a claim that we're better than everyone else, we have to justify that. It's not the other way around. So, everybody cool with this? What do we start? I'm claiming Mesa students are higher IQ than everyone else. So what are we starting with? We're not. The truth is, what you're going to start by assuming is we're not better. The evidence has to prove we're better. So we're going to start by saying, no, Mesa is just the same as everyone else, and potentially they could actually be lower. So where will we reject? Left tail or right tail? We talked about this yesterday. Where do you look to determine rejection?
The direction of the alternative?
Always in the direction of the alternative. So I have to be out here. Oh, okay. Meaning my evidence has to be overwhelmingly above average before you will conclude that we're above average. Does that make sense? If my evidence is above average but not overwhelming, then you'll say, you know what, there's not enough proof to say that Mesa students have a higher IQ. They're basically like everybody else. You with me on that? I want to keep this simple because that's exactly what we're doing. Now, I need to know what is the line in the sand. It's a one or a two-tailed test.
One tail.
One-tailed because the alternative is only in one direction. So we will reject the null if, well, first of all, the alpha level is 0.5. So what is the z that corresponds with exactly a 5% tail?
1.645.
1.645. And I think Ashad's got that memorized by now. Have we started recording?
Yes.
Okay, just me. Sorry.
It's just the detail.
Hey, he's got that memorized right, because that seems like the one we come up with the most often. Everyone thinks it's the 196. No, for confidence intervals, the 196 is the most common. But for hypothesis tests, most hypothesis tests are one tail. Most of the time. There are two tails, but most of the time it's one direction only. So that's why in a hypothesis test, this might be the most common value we use. Okay? So we will reject the null hypothesis if our measured value of z is what?
Greater.
Greater than. So we're setting ourselves up. We want to announce to the world, we want flyers, we want brochures on the Mesa College website. It says we are Mesa. We want it to say we are Mesa and we are better than you. We're really arrogant here. Right? Wouldn't that be cool if we could say that? We're better in every conceivable way, right? Our teeth are shinier, we're happier people, we're more fit, we're smarter, we're better to our moms. Well, right now we have higher IQs than everybody else. But we can't say that without proof. So we've set ourselves up. We haven't actually gone out there and collected a sample. So I want to make sure we understand there's an order of things, right? I have to set it up. Now we'll go out and collect the sample. So let's suppose that we went out and collected a sample. And our sample, let's say, we were able to get 48 people. And our sample mean was, let's say, 104.8. I'll just throw something out there. Now, it does not matter in this case. It does not matter what my sample standard deviation is. Why? Normally it does. Normally we need the S. Why does it not matter?
Because it's known?
Because we already know the population standard deviation. If we did not know the population standard deviation, then we have to use the sample standard deviation. Then it becomes a t-test, by the way. But because we know, right, we know this is sigma. That's not a mystery. So how do I do the test? The z calculation, well, yesterday what we did was we did the difference in the p's, the measured p and the hypothesized p. Now we're going to do the difference in the means. My measured mean and the actual hypothesized, right? The population is already 100. This is what our sample says. And on the bottom, that should look familiar. Or I should say, sorry, I've got the square root in the wrong place. Sorry, sigma over root n. We know this because we needed that for confidence intervals. Okay? Remember, the larger the sample, the bigger your z number is going to be because of this here. So this is the formula we use. we know mu, we know sigma before we start the problem. We went out and collected a sample, so we have determined the n, and our sample determined the x bar. We don't choose x bar. So our sample of size 48 had an x bar of 104.8. Okay? So, our z value, in this case here, is what? 104.8 minus 100 over, whoops, you put in the whole square root here, sorry, over 15 over root 48. Let's calculate this. This is a z value, so 2 decimal places is appropriate.
I got 2.22.
Does anyone else get that?
Yeah.
Good. 2.22. That's a pretty healthy z-score. Is it healthy enough? Well, let's see. My sample, am I in the shark-infested lava? Oh yeah, by a good measure. This is a good thing to do right here. My line in the sand was 1.645, and I had to exceed that in order to make a decision. We've clearly exceeded that. Conclusion time. Reject the null, fail to reject the null. Yeah, you're in the shark-infested lava. You reject the null. There's no gray area there. That's absolute. So we reject the null hypothesis. I always say there's two halves to the conclusion. Reject or fail to reject. Okay, that's the first half. Now, what is the truth? We're going to have a press conference later on today. We're going to announce to the world our findings. Well, because of the evidence, we've rejected the null hypothesis, and we're going to continue blah, 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 blah. I haven't said anything yet. The world doesn't know what the null hypothesis is, by the way. We do because we did the test. You have to understand, if I just say we reject the null, unless you were part of this process, you don't know what the null was. Oh, what's our conclusion? The alternative has to be the conclusion, and in words, what does the conclusion say? We are above average. So the conclusion is MESA IQs are above. Now, when you say above average, if our sample had come in at 100.1, that's above 100, but it's not enough above 100. So we'd say this is statistically significant. Have you guys ever heard that expression before? Statistically significant. I hear people use that in everyday language. Well, I saw this, but it's not statistically significant. They're usually throwing that out there without knowing what it means. This result is statistically significant because it produced a z-score that was out in the shark-infested lava. If this z-score had been smaller than this, we would have failed to reject the null because our evidence wasn't statistically significant. That's what statistically significant means. You had enough evidence to reject whatever the null hypothesis was in any situation. So far so good? Now the last piece of this puzzle is the p-value. I'd like to know if Mesa College students really aren't above average. Remember, if the null is actually true, then how likely is our result or one more extreme than our result? So in that case, the p-value, and again, in many scenarios, by the way, the p-value is the only thing people calculate. The p-value is the probability of z being what? Bigger than this, because look where my tail is. It's a result this extreme or more. So greater than 2.22. And that's equal to 1 minus the probability that z is less. Now let's look that one up. Go ahead and use your calculator. There it is. 2.22. What is this value?
0.0132.
That's really small. Here's what the p-value is saying in simple English. If the null hypothesis were actually true, then the probability of us getting a result this extreme or more is about a little more than 0.01. That makes you way more confident in your conclusion. You're saying, that means it's extremely unlikely that I'm going to get this result if MESA students really were only average or even below average. We're far enough above average that it was easy to reject. Now remember, if the p-value is smaller than alpha, you reject it. That means you're in the tail. If the p-value is bigger than alpha, that would mean you're on the other side of this. You didn't reject. And we looked at a lot of that last day and said, oh yeah, sometimes our p-values were really, really big. And again, the p-value sometimes helps you understand what you just said. We rejected the null. See, we did it at the 0.05 level. What if we had done this at the 0.01 level? Would we have rejected the null? If we had done this at the alpha equal 1% or 0.01, would we have rejected the null? No,
Yes.
because this is bigger than alpha. Oh, so if we had made our alpha level the 0.1, then it's 2.326, this would have fallen just short. That's what the power of this is. Now, before we did it, we said we kind of reserved the 1% alpha level for things that really are critical, life and death kind of things, pharmaceuticals, stuff like that. If it's just, Des and I have a bet, and we're going to compare. I don't think we need, 1%. I don't think we need that extreme. So we're saying, look, we're going to reject the 5% of the most extreme cases. And this would have been really extreme if it were not true. So we have very good confidence that we did everything right, and this is the right conclusion. Now, what made this problem nicer for all of us was I got to use Z. We're far more comfortable with Z. T is actually far more common, but we don't like T as much because there's two pieces of the T. I have to consider degrees of freedom, and then I have to look up the number, and for every degrees of freedom, there's a different number. You understand, at the 0.05 level, this is the only number that we ever have to worry about. Now look at your T-table for a moment. Just look, everyone pull out your T-table. If you're looking at your T-table, okay, see the one tail 0.5 level? Everybody find that? The 0.5 level? Now, how many values are there? Many. There's a different value for every degree of freedom. Oh, okay, with Z, there's no degrees of freedom. I just use that number. But with the T-table, depending whether I have 5 degrees of freedom, 50, 100, 200, I have a different number that I'm going to use in every case. People don't always like that, but you know what? In reality, it's not complicated. I just have one extra thing I have to think about. And the reason is, if I don't know the population standard deviation, which is actually probably the majority of things in real life, I have to use the T. The Z would not quite work. Now, back in the old days, particularly, when I say the old days, before everybody had access to computer software that would do things, when I first started teaching at Mesa College, this is what they did. They didn't use the T-tables. What they did was they used large samples. And if your sample is large, the Z value is close enough to the T value in the table that people would just use the Z because it was easier. But do you see the problem with that? It's not exactly the same. It's a little iffy. And if it was a close call, you might make the wrong decision because of the numbers being close. In reality, it's the T-table. I went back to school several years ago and did the master's program at San Diego State in statistics. And they basically use the T for everything. They hardly, outside of P, they don't use the Z at all. For mu, they use T almost 100%. This is the exception, this problem here. Okay, because this is one of the rare times we actually do know the sigma. So, let's do another one. All right. We want to test, we have a scale. I love using scales. We have a scale, and we'd like to know if it's accurate or not. That seems like a fair question. How do you know if a scale is accurate or not? This is a tricky one. How do you know if your scale is accurate or not?
You get a weight that you know is accurate and weigh it.
Okay, that's a good way of doing it. I have to have something where I already know what it is. You say, well, I weighed myself at the gym scale and I weighed this much. And then I went home to my bathroom scale and I weighed this much. They're not the same number. The only thing I can say is one of them is wrong. Could they both be wrong?
Yeah.
Yeah, so that's probably not the best way to take something where I absolutely know the weight of it. And now I measured on the gym scale or the other scale, and it's a little bit heavy or it's a little bit light. Okay? Now, I love tackling gym scales because I worked at a gym for years, and I would weigh myself literally once a year. And the gym scales always have the sliding balance thing, and you know it's going to be inaccurate. You know why you know it's going to be inaccurate? Because these things are ultra sensitive. And when you got on the gym scale, what do you always notice? The previous person always left the weight on there. You know, that 240-pound person left the thing all the way over, and so it's been sitting in this position for who knows how long, a day or two. Well, by the way, that completely wrecks that scale. It makes it inaccurate. It changes things. Think about like it's stretching or shrinking things. There's no possibility that scale is ever going to be accurate again when people leave the weights on. You can't fix that. So now you just say, well, this scale always weighs 2 pounds heavy. Well, actually, that's not how it works. It's not 2 pounds heavy. It's going to be in percentages, not pounds. How do you know? Because if you put a 2-pound object on the scale, it's not going to say 4 pounds. It might say 2.1 pounds. Oh, but the 200-pound person, it might say 202 pounds. You get where I'm going? So scales are a tricky thing. So let's say we want to know is accurate, period. And so I like Des's idea that we take things where we already know the weights. See, I did something just the opposite in the last couple of years. I used a scale that I was pretty sure was accurate, and I had purchased a bunch of weights. And then I weighed the weights on the scale to see if they were actually what the weights claimed to be. And the irony is none of them were. I have a bunch of 45-pound plates, and none of them weighed exactly 45. They ranged from 44 to 46. Now you say, well, how do I know it's not the scale? Because I put a weight on there, it weighed 44, and then the next one weighed 46. So even if the scale wasn't accurate, I do know neither one of those were the same. So yeah, weight is a tricky thing. I want to know if it's accurate. That's it. Now, can I assume that my scale, the accuracy is normally distributed and I know the standard deviation of all human beings that stand on it? Or probably not. Probably not. So this is going to be T ultimately. Okay? Now, what do let's say mu is going to represent the average amount the scale is off. Okay, and this, we'll do it in pounds. We'll make it simple. Because like at the gym scale, you're not weighing 2-pound objects, you're weighing human beings. And Dylan knows everybody's weight. He's the weight enforcer. He checks them on a daily basis. He knows everybody's weight. And then when he has them stand on that scale, he goes, this person was a couple pounds heavy, this person was a pound heavy. But maybe this person it measured a couple pounds light. Maybe for some reason this scale is just kind of wonky. Maybe, in other words, it's possible it went in each direction. So what we want to do is say, let's call mu the overall average of what it's off. So if exactly half the time it measures you a little bit heavy and exactly half the time it measures you a little bit light, the average might be right at 0. Which means it's not too bad. I mean, does that make sense? Let's go with that. So mu will represent the amount the scale is off. I'm trying to determine if my scale is accurate. So do I start by assuming it's accurate or it's inaccurate? Think about it.
Accurate.
Start by assuming it's accurate and see if the evidence tells us otherwise. Let's start by assuming my scale is not guilty. So let's start by assuming it's an accurate scale. But then if everybody gets on there, if their weights are way off, then clearly it's not accurate. So we would start with mu is 0. It's accurate. It's not, there's no difference. So what should the alternative be?
Mu does not equal 0.
Mu is not 0, yeah. Now, if my scale, if we did the average and we found the average was 0.01, aha, everybody's 1/100th of a pound off. That's pretty accurate. Yeah. I have a bathroom scale in my bathroom, and my son has one in his bathroom. Mine is just the old, you know, what do you call it? You know, the needle, yeah, needle, and he's got the little digital one. And they're usually about a pound difference, I think. I think his scale always weighs me a pound heavier, if I'm not mistaken. But there's times it weighed exactly the same. Like, how can I be a pound heavier one day, but exactly the same as my other scale another day? I don't know. So I'm thinking, well, one of them's not very accurate. Then if it seems if one's a pound heavy, shouldn't it always be a pound heavy? You know. But anyway, so this is our problem. And let's say again, we're going to test at the alpha is 0.05 level, because this isn't life and death. Now, I can't tell you the rejection criteria yet. Because if I say, well, okay, first of all, is it a one-tail or two-tail test? Two-tail test, so let's draw a picture. I will reject extremes in either direction. Great. And that means I need the T.025. I need to look that number up. So when you go to your table, look up T of 0.25. Why T? Because I don't have the population standard deviation. In fact, I don't even have reason to believe this is normally distributed. Oh. So when you look at your table and find the T value that corresponds with the 0.025 table. Can anybody tell me the value? There are many, yeah. And in actuality, if I use the computer, there are technically infinitely many values. There's a value for every value of n, isn't there? Oh. So I can't tell you the line in the sand yet. I have to know the sample size. So I'm designing the experiment, but I'm saying to make my life easier, I'm going to go ahead and determine the sample size. Okay? And just to make it simple, let's say we're going to go out and we're going to measure, and we've already decided we're going to use 30. We're going to use a sample of size 30 because we consider that a large sample. It probably wouldn't be a good idea to only do one or two. Do you agree? But there's actually a hidden thing here. And we've mentioned this before, we haven't dwelt on it. If you do not know it's a normal distribution, you absolutely have to use the t-table. But if you do not know it's a normal distribution, you have to use a sample of at least size 30, period. If you don't use a sample of size 30 and you use a smaller sample, then it's a completely different way of doing things. I referred to doing the crash test on the brand new Lamborghinis. We're probably not going to use a sample of size 30, probably going to be really small, but I can't use a t-table. That's called non-parametric statistical methods. At San Diego State, it's Stats 678, which when I was that was considered the hardest class at San Diego State for all majors. I took that class. It was gnarly, but it was actually really cool. We learned how do you do it when you have a really small sample. What if it's a rare disease? You can't have a large sample, right? How do you do things when you only have a few and you have no reason to believe it's normal and you have no population information? You have to do things very differently. That's the hardest problem that exists. We're going to avoid that one like the plague. Because we get to choose our sample size. We're not going to pick a small sample. We're going to pick at least 30 in real life because we cannot use the t-table if we don't. We can't use the z-table because we don't know if it's normal and we don't have sigma. In the first example we did. So we're gonna be smart and pick at least 30. That way we're covered. How many degrees of freedom?
29.
29. So look up in your table. Look up the magic t value. 29 degrees of freedom and 0.25 tail.
2.045.
0.25 in one tail.
Oh, and one.
That's the same as saying 0.5 in two tails, by the way. It's
Yes.
the same column.
2.045.
2.045. By the way, what would the z value have been? Wouldn't it have been 1.96? This is only a little bit more, isn't it? By the way, look at that same column on the t-table that you just pulled that number out of. Okay, you see the 2.045? Start going down the table. What's happening to the numbers? They're getting smaller and closer and closer and closer to 1.96. In fact, at the very bottom of the table, they are 1.96, aren't they? That's the benefit of the t-table. The larger the sample, the closer to the normal distribution it becomes, even if the population is not normally distributed. This is true in reality. No matter what you're sampling, if your samples are large enough, your sample means we show, that's called the central limit theorem. We did that a couple months ago. Your sample means become normally distributed even if the population is not. The larger your sample, therefore the more you can trust your results. That's a good thing. So this is going to be the line in the sand. It's a little bit bigger. So in other words, we're making it a little bit harder to reject because we don't have as much information. So what is my criteria for rejection? I will reject the null hypothesis if, now it's the measured value of t. Look at your picture. If t is what? Less than
Less than-
Negative.
Mhm.
negative 2.045 or positive 0.2. So in other words, this is the negative, this is the positive. I will reject in either tail. I'm not going to reject the main body, I'm going to reject the tails. It's very, very important that you have these inequalities in the correct direction. If you have in the wrong direction, that means you're going to reject all outcomes. No, I only want to reject the extreme outcomes. Now let's go out and collect our sample. In reality, a lot of folks don't realize there has to be an order of things. Collecting the sample is the last thing you do. Because you have to set up the theory and the experiment. Now, how hard is it going to be to collect the sample? It's going to be easy. Like Des says, we take things where we already know the weight and we weigh them. Or we can make it simpler. Let's say I have a digital scale that I have absolute faith in. And so I have Graham step on the digital scale, maybe 1 decimal place. And now I'm going to have you step on the scale that I'm actually testing. Everybody cool with that? Now, the difference in weights is what I'm talking about. Okay? And we're going to average all of those distances. So we can do it 2 ways. Des' suggestion of taking objects where we absolutely already know the weight, or taking human beings and weighing them in something where we trust it and then weighing it on the scale. It doesn't matter which way we go. I like doing the human beings on 2 scales simply because when Des talks about weighing something we already know, it's probably something small, isn't it?
Yeah.
You know, I have a 10-pound weight and I know it's exactly 10 pounds. But a 200-pound person, a 10-pound weight, even if the scale's not good, are we going to see much difference in a 10-pound weight? We might see a 1/10 of a pound, 100th of a pound. But the 200-pound person, we might now see a couple of pounds. So I think it's probably safer to take heavier things, like humans, than objects where we know the weight. What you're describing is perfect if I have a smaller scale, a little simple balance scale. So we have the means of weighing somebody on a digital scale that we know is correct because we've tested it already. And now we're going to go on the gym scale where the big guy always leaves the thing slid all the way in one direction. You guys know what I'm talking about? I have never in my life ever seen a gym scale where it was reset. My chiropractor has one of those scales in his office. And every time I've ever gotten on it, it's always in one direction. I go, you do realize this thing is worthless. And his is several pounds off. I mean, it's actually, and how do you know that? Because when you go back to 0, what happens? It's always tilted in one direction. So you might have to start it at 3 pounds just to get it level. Well, now the question is, does that mean it's 3 pounds off, or is it going to be a percentage off? And I throw my hands up because I don't know for that scale, but I don't trust that scale. So we want to do this. We went out now and collected a sample. We went out and collected a sample of size 30. Our X bar, our average off was 0.046 pounds, and our standard deviation was, let's say, 0.012 pounds. Why am I telling you S? I didn't tell you S last time. Because we don't know sigma. So we have to use S. Ooh, we have to use S. We don't have a choice. Now, the Z calculation that we just, I have it right over there. The Z calculation is right there, okay? We don't have sigma. So we use T, and what do? We still do this. We still do this. So what goes here? S. Yeah. That's why it is a T calculation, because we're using S and not sigma. and we don't know if it's normal or not. But because we don't know it's normal, that's why we have to have a sample of at least 30. Are these the same formula? Yeah. They're the same formula, but I'm using an S instead of a sigma because I don't know it. So I have to use my measured value. And here's the thing, a population standard deviation is what it is. But when you take a sample, it only takes one value in your sample to upset the sample standard deviation. And interestingly enough, I had a student come by my office yesterday and he was talking about it. He says, yeah, his physics class, I just had a test and the teacher posted the mean and standard deviation. I laughed, I go, does anybody in the class actually know what those mean? He said, no, because none of us have had statistics. But the instructor posted though, he goes, I didn't really, and I explained to him how to interpret the standard deviation. I said, why is your instructor posting the standard deviation of your physics test? Just to show how spread out the scores were. And I thought it was interesting to do that in a class where nobody knows what that means. But said he posted it, but there was only like 15 tests. So what does that mean? Well, what if you have 15 tests and 14 of them are really good and one of them was terrible? That means your standard deviation is going to be large when it should be small. Because most of the scores are grouped together, but the one extreme score. Remember, think of income, housing, because it's skewed. Right? It only takes one Bill Gates to totally mess everything up, and it also makes the standard deviation look way higher than it really is in a sample. But if I'm talking about the population, extreme values aren't going to make a difference. You're talking millions and millions and millions. But if I'm only talking a small number of examples, right, one extreme value can really mess it up. So that's why it's a little more conservative. So in this problem here, let's put the numbers in. So what do we got? We got 0.46 minus, what's our hypothesized value of mu? 0. Oh, and by the way, do write it in there. A lot of times when we're doing stuff, a lot of times our hypothesized value is going to be 0. I'll explain what that exactly means. And then what goes here? 0.12 over the square root of 30. Let's do this calculation, shall we? Tell me when you get a number.
I have 0.6 or 0.70, I guess.
Does anyone else get that?
About 21.
Double check something. Your
I got
130 might have been on the
20.
wrong place.
Yeah,
20.9.
9. So you got into 2 decimals. Actually, it's this, isn't it?
21, yeah.
What do you think? Look at my picture. Where did we fall? Probably, what, the end of the hallway? We're going to reject for a T of just over 2, and we got a T of
Oh, I see.
21. Rocket launched into the Shark Infested Lava? With NOS. You know, like, right, Fast and Furious, got the NOS. So you have your rocket and you turn on the NOS and you're like a million miles away. Does this make it easy for a conclusion? Yeah, it's real easy. What's our conclusion? Reject the null in words. This is a numerical measurement because we have to compare something. We need numbers. What does my alternative actually say? The scale is inaccurate. So your conclusion should not be reject the null, mu is not 0. Yes, mathematically that's a correct statement. Well, what are we saying? You're going out to the public. There's cameras everywhere. There's thousands of people hanging on your every word. And reject the null, mu is not 0. Oh, everyone goes away happy, having no idea what that means. No, you say, the scale is inaccurate. That's your conclusion. Reject the null, the scale is inaccurate. A lot of the books will actually mince words, and I don't like this. They'll say, reject the null, there is significant evidence to make the conclusion that the scale is not accurate at the 1%. That's kind of like in a court of law. It's guilty or not guilty. Well, there was enough evidence to conclude that it's reasonable to assume that they were actually guilty, blah, blah. No, they're guilty. Don't mince words. Don't water it down. Don't make it sound like it's ambiguous. Don't make it sound like you might be wrong. Does everybody understand what I'm getting at? We did a test. We set the line in the sand. We exceeded it by quite a bit. The conclusion's absolute. You don't say it might be. It's probably true. It's probably true that you're guilty, and we're going to give you the death sentence because you're probably guilty. I think we'd all have a problem with that, wouldn't we? No, you are guilty. Now we're going to do the sentencing. You don't say you might be. You're most likely guilty. Right? It doesn't work that way. No, you're guilty or you're not guilty. We reject the null or we don't reject the null. We rejected the null, and in fact, it was real easy to reject the null. Now, here's where it's a little bit trickier. P-value. Because I can't find the p-value in the same way. So we state p-values a little different with t's and chi-squares. What was our level here? 21. Now go back to your t-table. Our value of, where are we? 29 degrees of freedom. Okay. Our value was pretty extreme. Okay. What's the smallest number you see in the up at the top of B, 0.005. The tail of 0.005. Remember, if the p-value is smaller than the alpha, you reject it. Is our p-value smaller than this? Yeah. Our p-value is going to be smaller than this. Why? Because we're a million miles. What's the probability of a result that extreme or more? Pretty microscopic. But the problem is I can't look up that number. So what I do is I just look up the highest, the biggest number on the table. Okay. My z was, or my t was pretty far past the 2.756, which is the biggest one on there. So we would say our p-value, we write it like this. Our p-value is simply less than 0.005, because that's the smallest it could be on the table. In reality, our p-value is probably 0.000000, a lot of zeros. Remember, our t was 21. But that's, unless we have a computer in front of us. And by the way, if you had a computer in front of you and you knew how to do this on the computer, which by the way, nobody does, because this requires really powerful software to do stuff like this, you would come up with a p-value that had a lot of zeros. So the best we can say is, it's just smaller than this. On the z table, I can give you a number. But what if on the z table, we've done this before, what if on the z table, your z value that you calculated is astronomical? Your z value was 21. Then when you go to the z table, what does it say? It says less than 0.0001. On your z table, it tells you to use that. Right? So we're doing exactly the same thing. We're just saying, let's use the smallest number we have in front of us. That's it. Okay?
Wait, I'm sorry, where did we get the 0.005 from?
Oh, look at your t-table.
Okay.
Look at the top. Look at the alpha levels. Those are the tail probabilities.
Yeah.
What's the absolute smallest one on there is the 0.005. In reality, if I could do this on a computer, it's probably 20 zeros after the decimal point. I mean, it is so absurdly small. The answer can never be exactly 0, but for all practical purposes, it's 0. What's the probability that if your scale is perfectly accurate, what's the probability of a result this extreme? You're more likely to get hit by lightning 3 times in the next 8 seconds. You know, that kind of, it's absurd.
So we don't bother doubling it, right? Because it's still,
Well,
we know
it's smaller than this. Yeah, yeah,
Right.
it's so, yeah. The t and the chi-square, you're still asked the question about p-value. You just can't give me an accurate number looking at the table. You can give me an accurate inequality. And we don't love that, but it's okay. You're not a statistician yet, so you don't have access to the software required to actually do that calculation. We don't need to. We just want to understand a logical way of expressing ourselves. Now, I gave you an absurd example. I mean, it was so extreme. But sometimes that makes it really easy to make conclusions, doesn't it? I mean, we don't mind extreme. All right. Now, let's check on our tires, okay? A tire manufacturer claims their tires last, keep it simple, 40,000 miles. That's kind of the universal starting point. I recently purchased tires for my car, and my tires were bald, and my car's on its last legs. I didn't want to get nice tires. I just wanted something that I could survive on. So I went to the tire place, and I said, look, I don't want expensive tires. You know, look at my car. It's held together with duct tape. No, and so the guy said, okay, these tires are good enough. They will last longer than your car. They were the 40,000 mile tires. That's generally the lowest level. I've had tires that were 60,000 or more. And the nice thing is they're guaranteed. So if they do fail prematurely, you do okay. You know, you get them prorated, you get your next set really cheap. Or in some cases, I've had tires wear out so fast that they actually replace them for free because they wore out ridiculously fast. I mean, 10,000 miles in, they were already having tread issues. They're like, yeah, we're just going to give you a different set altogether. You know, you're not happy with that because it means they sold you the wrong set to begin with, and that's what they told me. They said they sold me the wrong size tire for my car. I had to go to a tire place where that's all they do all day, and they give you the wrong size tire. I didn't ask for a particular size. They fit them on my car, and it was the wrong size, so they wore out. 60,000 mile tires wore out in 10,000 miles. Yeah, that's crazy. And by the way, I don't drive like a 16-year-old. Sorry, guys. You know, I probably drive closer to old man status than I do, you know, teenager status now. So they claim their tires last 40,000 miles. That's totally reasonable. But you're the Department of Weights and Measures. You are a government organization that oversees truth in advertising. There is actually such a thing. And you keep getting anecdotal results. I mean, you know, you get that complaint that says, I bought these tires and they didn't last this long and that company is not making it right. That's where the complaints would come from. And there have been so many complaints about these particular tires that now as the Department of Weights and Measures, you're going to step in and say, we're going to test them ourselves. And by the way, if they fail the test, well, first of all, you have to change your claim. You can't claim they last 40,000 miles. That's truth in advertising, because they don't. But does the tire company have to prove they last 40, or does the government have to prove they last way less in this instance?
The government has to prove the last way less.
Yeah, the burden of proof is on the government because these are already out there. And by the way, this is not an absurd claim. This is kind of standard, but it may turn out that they were lousy. You know, it may turn out they're lousy. So this is the situation. Now, if they say they last 40, but what if the government tests them and they last 45? They're lying. Oh, wait a minute. Is it okay if they're better than 40? It's only bad if they're worse. You understand? So this is one of those implied inequalities. The null hypothesis is that they last exactly 40. But lasting more than 40 is okay. If you make your null an equal and your alternative a less than, then half of the possible results you've excluded. So what happens if your test results come in better? You see what I mean? Oh, so it's way safer to say the null hypothesis is what? That the mean life of my tires is, in words, at least 40,000. Even Triola does an equal sign here, but he doesn't really tell you what happens if your results come in better. That's why I like the greater than or equal, just in case. When we did the Mesa College IQ thing a little while ago, we'd say, well, we're going to start with the assumption that Mesa students are average and make you prove otherwise. But what if it turned out that Mesa students were actually below average? That wasn't one of the possible outcomes. That's why the null should not be equal, but less than or equal, just in case. We're trying to prove they're better. Not better means same or worse. That's why it really should be. These really should always be complements. So what's the alternative? Now, how much less than do they have to be? A lot. If they're only a little less, we'd say that is not statistically significant. That's what that term means. I gotta be in the tail in order to make a conclusion. So in this case, if I agree, I'm going to reject here. And now I don't know what that value is, It depends how many tires I test. Now, let's do something different. Let's test at the 01 level. And you know why we're going to test at the 01 level? Because the penalty is so severe. The penalty is so severe if it's concluded that there's false advertising going on here, that we want to make darn sure. We're going to make it harder. By making the alpha 0.01, we're making it much harder to reject the null. We're making it much harder to find them guilty. That way, if we actually do find them guilty, we have no doubt we did the right thing. Does that make sense? So we're making it much, much harder in this case here. Now, so we're going to go out and, so Ashad, you're the one running the show, working for the government, so you're going to buy one set of tires, put them on your sports car, and drive them until they wear out. What do you think?
That's not enough data.
Is that going to work? Okay, first of all, not nearly enough data. You're putting these tires on your sports car. Might they wear out a little faster than if you put them on your SUV, your minivan? You know? Yeah, maybe we should, the more data would be better. How about all sorts of cars? Do you agree with that one? Many years ago, I had I love that car. I had an Acura Integra. That was in the earlier days of Acura, so it was actually really affordable. Really affordable car. And I could drive 80 on the freeway, and I got 35 miles a gallon driving 80. It was the most unbelievable. The thing was just purred like a kitten. And they gave me really nice tires when I bought the car. They lasted 20,000 miles. My next two sets each lasted over 60,000 because the tires that the car came with, and by the way, this is pretty normal. The tires the car comes with are usually absolute garbage tires. Garbage. And they're like, oh, these are sports racing. It turned out when I went to replace them, like, God, never put anything like it. They were garbage tires. They lasted 20,000 miles. Well, my son has a brand new car, and he drives it very carefully and all this, and his tires lasted 25,000 miles. It's the tires they put on his brand new car. So those aren't the tires we're testing, are they? But the point being that, I like what you said, more data. How many tires do you want to test? Money is not an issue. We're the government. Here's the problem, though. How do you test tires? You guys don't know how tires are actually tested? So Petra's going to test tires, so every time you get in your car and you drive around town and you go home and you turn off the car, you make 10 miles at a time, 20 miles at a time. No, you know how tires are actually always tested? On an oval, racetrack. So you drive for 12 hours, and then you drive for 12 hours, and then you drive for 12, yeah, that's how they're tested. Just continuous driving. How the heck are you going to get 40,000 miles on a set of tires if you're driving it occasionally? It took you 3 years to do that. I need to do it in a short period of time. Oh, now, if I'm driving around a track constantly, would you say that's more or less wear and tear than a normal driving?
Less
Significantly less, because what aren't you doing?
braking.
Braking. That wears tires out faster. Oh, okay. So there are some conditions we'll throw in here, but we're also going to run them down to the ground. And by the way, are we going to run them until they're bald? No, we're going to run them until they're worn out. You never drive until they're bald. You drive until the tread is less than a certain amount. I don't know. What is it, the head of Lincoln on your penny? You guys know that one?
There's the marker, isn't
If
it?
you take, well, but if you actually took a penny and put it in the tread, if it doesn't reach Lincoln's head, they're too worn out. That's what they do at the tire places. That's like the simplest quick check. If they go out there and they're completely bald, bad idea. That's a horrific accident waiting to happen. No, you replace your tires long before they're bald. But the idea is you're already in better conditions, so you're also maybe not going to run them until they're bald. But we're going to do lots of tires. How many tires are we going to do, guys?
200.
200.
200 cars or 200 tires? Yeah, because you can't, let's do 197 tires. They kind of need to come in multiples of 4, don't they? So I like, heck, let's do this. I've got a lot, let's do 1,000. Let's do 1,000 tires, that's 250 cars. Can we be pretty certain, whatever results we get, can we be pretty certain that they're going to be accurate results either way? Yeah. So we're going to test 1,000 cars. Now, when I look at my table, I don't have 999 degrees of freedom. But do you know at 999 degrees of freedom, you're not going to have a different number than you are at 1,000 degrees of freedom. They're not going to differ until about the 6th or 7th decimal place. So can I use the 1,000 degrees of freedom number? Oh, yes. Now, when I go farther up the table, I see differences in the numbers as I move, but not a lot. And here's what I mean. Look up your tail, look at 39 degrees of freedom, look at 40 degrees of freedom. And by the way, we're at the O1 level. At 39 degrees of freedom, the O1 level is 2.426. 40 degrees of freedom is 2.423. They differ in the 3rd decimal place. As I go further down the list, they start differing by less and less and less. By the time I get to 1,000, if I went from 1,000 to 1,001, they probably don't differ till like the 8th or 9th decimal place. In other words, it isn't going to make a difference at this point. So there's 999 degrees of freedom, but I can certainly use the number for 1,000 because it's not going to be different to 3 places. Everybody cool with that? Okay. Excuse me. I mean, just look at from 1,000 to 2,000. It only differed by 0.003. So 1,000 to 1,001 is probably going to differ by 0.000001 or something. So what is the number we're going to use? Now, it's a 1% tail, and we're only going to reject the left end. Okay? So what is the t value that's going to correspond with the 1% tail?
2.330.
2.330. By the way, that's really close to 2.326. It's really close to the z value, isn't it? In fact, if I go a little more, it'll become the z value. 2.330. So I will reject the null hypothesis if my measured value of t is what?
Greater than, oh, less than.
Less than what?
Yeah.
Less than negative
Negative
2.330.
2.330.
If I do it for greater than, then I'm going to reject the greatest tires in the world. No, I want to reject the worst tires in the world. Everybody cool with that now? Now, we're going to go out and test 1,000 tires. I am pretty sure that we're going to get this right. So, Ashad has hired a whole bunch of people to be his drivers. And he's in a small town, so you don't have a lot of choices. So yeah, you had to hire a couple of 16-year-old boys. Why am I pointing that out? Because the worst drivers on planet Earth are. How do you know that? Insurance. But you also hired a couple of 80-year-old, grandmas, and a bunch of middle-aged folks. In other words, you hired people that are extremes in every direction. Extreme safe, extreme dangerous. You hired everybody under the sun. You know why that's a good thing? Because isn't that drivers in general? In other words, aren't drivers everything? So you have everybody driving. The extremely safe, the extremely unsafe, the crazy person who takes corners too fast, the person who takes corners too slow. Are we going to get an accurate picture if we do this? Yeah. And isn't that the whole point? It might sound, well, why don't I just hire professional drivers who are really safe? Because they will make the tires last longer than they probably would when you're driving. That's why it's, Does anyone know what the EPA is?
The Environmental Protection Agency.
They are the ones, when you see a car commercial, and whatever the car is, they always give you the gas mileage. And they say, EPA, 32 miles a gallon. You guys ever seen that? My whole life, that was always a major thing in a car commercial. That was usually one of the first things that they'd tell you the gas mileage on the car. I have a car where when I bought it, it says the gas mileage is 30. My gas mileage is about 20 miles per gallon. EPA estimates, are they accurate? No. Are they close? No. Not even a little bit, but they're for comparison purposes only. Why? Because the EPA takes the engine out of the car and runs the engine until it runs out of gas. How many of you drive around with just an engine and no car? The engine will go much farther if there's no car to pull along, no weights, no friction. Do you understand what I'm getting at? It is a completely artificial, impossible situation. So what they do is they take an engine out of a car, fill it up with gas, run until it runs out of gas. And by the way, you should get exactly the same amount of miles every time you do this. because you're never actually driving the car. And then they will use that number for EPA estimates. No human being could get that mileage because, well, now you have a car, it's really heavy and, you know, you have driving and you're going faster and slower and you're pressing the gas, you're pressing the brakes. But the EPA numbers are so you can compare it to other cars because it's the same organization that sets these numbers. Oh, so if that one says 35 and that one says 40, that one's going to get better mileage. But when you actually drive it, it's going to be much less, just so you know. So the point being is that sometimes the numbers that we're seeing aren't necessarily accurate numbers. Okay, so we went out and we collected, where is it? We collected this. Here's what we saw. I'm just getting nice big round numbers. And this is miles. Okay. Now let's see what we get. All right, let's see what we actually get here. So our T is what? It's 39,843 minus 40,000 over 1,046 over the square root of 1,000.
Negative 4.75.
Approximately negative 4.75. Does anybody else get that? What do you think? Now, you said, but that average is so close. You just did 1,000 tires, and your average was less than the claim. That average needed to be greater than the claim, or at least right on the claim. Now, is it hugely less? Now, think again, I want you to think about it. You ran tires until you couldn't run them anymore, and they were not getting 40,000. They were falling short. This is an issue, clearly. So this is less than negative 2.330. Therefore, we reject the null hypothesis. What is the conclusion? In words, always in words.
The tires last less than 40,000 miles.
Perfect. The tires last less than 40,000. So, you're the tire company. What do you say? You can't, by the way, first of all, you wouldn't guarantee to get 40,000. Do you know why it would be a bad idea to guarantee 40,000? Because that means most of the time people aren't going to get 40,000. By the way, will some people get 40,000? Of course. But most people won't. So that means you're going to be replacing a lot of tires. So what do? Do you say your tires are going to last 39,800? No, you say things like, with proper driving, you may get 40,000 miles. You change the wording so you're not guaranteeing. You may get this. Now, think of commercials. Do you hear commercials where instead of a guarantee, they say you may get this? There's some pharmaceutical out there for some terrible condition that you see, and they say you may get relief. You may get relief from this, and that's true. They're not saying you will get relief. They're saying you may get relief. Now the problem with may, what percentage is may? Is that 1%? Is that 99%? You know, go to the party, Des, you may have a good time. But what does that also mean? You may
May not.
not. So it's a little bit ambiguous, but it's, here's one I hear a lot with commercials. They'll say, you know, how long we've been around. This is a company that's been around for nearly 40 years, or nearly 50 years, nearly 100 years. You'll hear things like that all the time. How close is near? I don't know. If I said, you know, our company's been around for nearly 40 years, and we've been around for 30 years. Is 30 years near 40 years? I guess you could say that. But I think you'd be safer if I said, well, we've been around for 39 years and 9 months, you know. But people can make statements like that with it being a little bit vague because they're not saying it is, they're saying it's in the ballpark. This is a tricky one right here. This is a really tricky one. I purposely made this one not work. You go, but it's so darn close. You're right, it is so darn close. But really what's happening is people in general, people are not getting 40,000. If the mean is that, then that means that most people are not getting 40,000. Now, are they getting way less than 40? No, but the problem is I want to still say 40,000 mile tires, so I'm going to have a warranty that prorates the tires. Knowing that, you know, Dylan's going to come in, you're 1,000 miles short, right? Chance comes in, you were 500 miles short. David comes in, you were 2,000 miles short. Des comes in and goes, hey, I got 42,000 miles. Great. That's what that's what we were hoping. There are going to be people that get more. But the majority of people are going to get less. Now, you're the consumer. At 39,000 miles, it was time to replace your tires. Are you going to say, I feel robbed, I feel cheated? Or are you going to say, well, maybe I just drove a little bit, you know, rougher on these tires than I should have? Maybe that's you say, you know, I do a lot of stopping and starting and I slam on my brakes a lot. I drive in such a way that the tires very well could have wore out prematurely because of the way I drive. Okay? So what do they always say in tire commercials? Standard wear and tear. In other words, normal driving conditions. Oh, okay, because what if you're just, you know, that crazy person who takes everything too fast, you know, every corner too fast, and you slam on your brakes? Yeah, you're going to wear your tires out faster. That's not normal driving conditions. So here's a perfect example. This is how you test things. This is how it's actually done. And I like what we said earlier. We want this number to be as big as we can possibly have it, so any conclusion we make, we are certain. We are totally certain of that conclusion. Okay? Everybody good with that? All right, let's take a break.